Now we'll start the APC 2-7 section of the video. Constant acceleration, a special case. It's where the acceleration stays the same the whole time. That means the velocity is changing, of course, but the acceleration stays constant. In many types of motion, the acceleration is either constant or very close to constant. You might accelerate a car at an approximately constant rate when a traffic light turns from red to green. The graphs that you might encounter are this, and I'm going to talk about the acceleration graph down here first. You'll see that the acceleration is constant, it's flat all the way across. It's a positive acceleration, so if you go up here to the velocity versus time graph, you'll see that the slope of that velocity versus time graph is constant. It stays the same the whole time, and it's a positive slope. And over here, you're going to see the slope varies, but it varies at a constant rate. It changes at a constant rate, and it's a parabolic curve, actually. So here's a possible set of graphs for an object moving at constant acceleration. And we see the acceleration graph is horizontal. So you'll recognize the set of equations we use for solving problems dealing with constant acceleration from your past physics class. And here's a list of them again. You'll want to write these down. You want to pause the video and write these down in your notebook. Sometimes this right here, this x minus xo, you'll see that written as delta x. It's just easier to write that as delta x. So you'll see that x minus xo as delta x equals v of t plus 1 half at squared. Or you'll see this v squared equals vo squared equals 2a delta x. So you want to make sure those are in your equations list in your notebook. So pause the video now, write those in there. Another important thing to realize is that these equations are all derived from each other. If you take a derivative of or an integral of one equation and do some algebra, you end up with another equation. So they all can be derived from each other, plugging one in for another, doing substitution, and so on. The textbook shows it nicely how that all works. So let's go ahead and try this example here. It says an electric vehicle starts from rest and accelerates at a rate of 2 meters per second squared in a straight line until it reaches a speed of 20 meters per second. The vehicle then slows at a constant rate of 1 meter per second squared until it stops. So let's go ahead and find how much time elapses from start to stop. So let's go ahead and pause the video, see if you can use those equations to find this. What you want to do is write down your givens first. So it starts from rest for an initial velocity of 0. And then accelerates at a rate of 2 meters per second squared. So you write that down next. Acceleration equals 2 meters per second squared. That's a positive 2 meters per second squared. Until it reaches a speed of 20 meters per second. So that's our final velocity equals 20 meters per second. The vehicle then slows at a constant rate of 1 meter per second squared until it stops. So now, in our second section, we have an initial velocity of 20 meters per second. Our final velocity now is 0. And we have an acceleration of negative 1 meter per second squared. So we want to know how much time elapses from the start to the stop. So this is really two problems in one. We have to find out how much time it takes in section 1 and how much time it takes in section 2. So you have to find the time here and the time here. So let's go ahead and try that. Pause the video, see if we can come up with those two times, and then we'll add them together to get our final time answer. So go ahead and you plug it into, looking at those four variables that we have, we're going to use v equals vo plus at. So you go ahead and plug those values into your equation there, and you'll see that the time, the first one, if you plug that all in, the time in your first one is 10 seconds. And if you go ahead and plug in over here, you plug in your four variables, you'll end up with your time, in this case, equaling 20 seconds. So we have to remember that they want the total time, so that's just the two added together to give me 30 seconds. So that's your answer there. The next question, part B, is how far does the vehicle travel from start to stop? So again, it's two questions in one. We want to find the displacement in the first section, delta x. And if you look at those variables that you have written down, and actually, why don't you pause the video look at the variables that you have and see what you can come up with for an answer. Remember, we want to solve for delta x. So in the first section, well, there's actually, because you have so many variables, there's a few different ways of doing this. Let's go ahead, and a nice easy way might be delta x. I'll do two different equations, so each using two different ones. Delta x equals VOT plus 1/2 a t squared. We go ahead and plug in our values. Delta x we want to solve for. Our initial velocity in this case is 0, so that just whole thing goes to 0. Plus, now we have 1/2. Now the acceleration in the first part is 2 meters per second squared. And that had occurred for 10 seconds. That has to be squared. So we end up with an answer of a distance of 100 meters. So now we go to the second part here, and let's go ahead and we can use the equation. We could have used the delta x one again. Let's just try this one. V squared equals VO squared plus 2a delta x. Our final velocity actually is 0, so that's good. Our initial velocity we know is 20 meters per second for this first part. That's squared. Our acceleration in this case is a negative 1 meter per second squared. We want to solve for delta x. So if we go ahead and solve for delta x, we end up with 200 meters. Again, we have to add those together, get our final answer of 300 meters.